Hi, welcome to Chapter 10, Gases, Overview Part 1, where we're going to talk about characteristics of gases, pressure, some gas laws, the ideal gas laws, applications of the ideal gas law, and partial pressures. So characteristics of gases. The physical properties of gases are all very similar, and most gases contain mainly of non-metallic elements with simple formulas and low molar masses. Unlike liquids and solids, gases will expand to fill their container. They're highly compressible, and they have extremely low densities. Two or more gases can form a homogeneous mixture. Properties that define the state of a gas sample are, you have to know its temperature, its pressure, its volume, and the amount of gas, which is usually in moles. So let's talk about pressure first. Pressure is the amount of force applied to a certain area. So it's force over area, where your force is measured in what we call newtons, which is equal to a kilogram times a meter per second squared. And A is your area in meters squared. Atmospheric pressure is the weight of the air per unit area. So here's a picture. You have a column of air that's 1 meter by 1 meter, and it's basically sitting here, and the gravitational force is pulling it down, and the weight that exerts would be your atmospheric pressure. The units of pressure. The SI units, or metric units, are the pascals, and 1 pascal is equal to 1 newton per meter squared, because remember, it's force over area, and force is measured in newtons, and area is in meters squared. This is equal to 1 pascal. There are many different units of pressure. Another one is called a bar, and 1 bar is equal to 10 to the 5 pascals, or 100 kilopascals, where this K is kilo. We also have millimeters of mercury, or torr. The numeric value when you have both of these units are equal to each other. 1 torr is the same thing as 1 millimeter of mercury. A millimeter of mercury is basically, if you look down here, if you have a dish with mercury in it and a tube, you measure the height of the mercury in the tube, and that equates to the pressure. And you measure the height in millimeters. So it's literally millimeters of mercury. Atmospheric pressure, what you call 1 atmosphere, is equal to 760 torr, or 760 millimeters of mercury, or 101.325 kPa, or 1.10325 bars. Okay, write these down somewhere, because you're going to have to convert from one pressure to another, and you're going to have to know them. Another way to measure pressure is called a manometer, and it uses the difference in pressures between the atmospheric pressure and a gas in a container or vessel. Okay, and by looking at the height of the mercury in your tube here, you could kind of determine the pressure. So how do we do that? So if we look at this first picture here, so you have a gas in here, and you have atmosphere pressure pushing down. We call that P atmosphere. I'll call this P gas. If the height in this U-shaped tube is higher on the atmospheric side, that means the pressure that the gas is exerting is greater than the pressure of the atmosphere. So it's pushing the liquid up higher. So that means the pressure of the gas would be your atmospheric pressure, which in this example they say is 755, plus whatever this height is, and this height is 24. Now in this example, the liquid in the tube is higher, closer to the pressure vessel here. So that means the atmospheric pressure is pushing down harder, pushing the liquid up here. So that means the pressure of your gas is less than your atmospheric pressure. So what you do then is take your atmospheric pressure minus the height difference in the U. So throughout this chapter, we're going to refer to something called STP. It's standard temperature and pressure. Standard temperature is 0 Celsius or 273 Kelvin. Remember, to get from Celsius to Kelvin, you take your Celsius, add 273, and you get Kelvin. Normal atmospheric pressure at sea level is referred to as your standard atmospheric pressure, and that is equal to any of these pressures with these units. Notice how many different pressure units there are. So one of the first gas laws we're going to talk about is Dalton's law of partial pressure. And basically what he said is that if you have a container with more than one type of gas, the total pressure in that container is the sum of the pressure from each gas. So if you look at your picture here, you have your blue gas here, and that is exerting a pressure P1. And here you have your green gas, and that's exerting a pressure of P2. And if you look at your gauge up here, P1 is 1 atmosphere and P2 is 2 atmospheres. So when you mix the two together, the total pressure, if you look at your gauge here, is 3 because it's 1 plus 2. So if we want to write this in a equation form, your total pressure is the sum of all the partial pressures. The pressure of each individual gas is called the partial pressure. Pressure of each individual gas. Now, what if you don't know the pressure of the gases, but you know how many moles are in there of each gas, and you know the total pressure? Well, then you could rearrange the equation where you take the moles of one gas that you're interested in, divided by the total moles of all the gas, times the total pressure, and that'll give you the partial pressure of whatever gas you put on top of your ratio here. Or another way to write it is the pressure of gas 1 equals the moles of gas 1 divided by the moles of all the gases, the total moles, times the total pressure. And this ratio of moles here, sometimes we represent with an x1. That's a mole ratio. So one application of this partial pressure is when we are collecting a gas over water. So here is an example. You're generating a gas and you're collecting it over water. So the beaker was filled with water. As the gas bubbles up, it pushes the water out and you collect gas on top. But the problem is you're collecting the gas you generated in your experiment, but you also have water vapor gas in there too. So now you have two gases and you don't really care about the pressure of the water vapor. You just want to know the pressure of the gas you produced. So in order to kind of get rid of the partial pressure of the water, so here's another example. Here we have zinc and we're adding hydrochloric acid. It's producing hydrogen gas, which we're collecting here. And if you zoom in, you see you have water vapor and you have hydrogen. Okay, you just want to know about the pressure of the gas, the pressure of the hydrogen here. So as it turns out, your atmospheric pressure is equal to the pressure of the gas plus the pressure of the water vapor. This pressure of the water vapor is tabulated already for you. So you can look it up in a table, which are called water vapor tables. All you need to know is the temperature. So at a certain temperature, you're always going to have so much water vapor in the air. So then you can subtract that. So you can rearrange this and get that the pressure of your gas is P atmosphere minus the pressure of the water. So let's look at a couple examples of how to calculate partial pressures using Dalton's law. So it says here, if the total pressure of a container is 1.02 atmospheres, and the gas inside is made up of 27% oxygen and 73% nitrogen, what is the partial pressure of nitrogen? Well, this percentage here is your mole fraction. So 73% of the air is nitrogen. So you turn your percentage into a decimal, multiply it by the total pressure, and you get that your partial pressure of nitrogen is 0.74 atmospheres. In the second example, they're giving you the moles. They say that a container that has a total pressure of 1.5 atmospheres contains 5 moles of oxygen and 2 moles of nitrogen. What is the partial pressure of nitrogen? So you need to take the moles of nitrogen, which in this case is 2, divided by the total moles, which is 7, times the total pressure, which is 1.5, and that'll give you the partial pressure of nitrogen gas using your mole ratio. So some gas laws you might remember from your sophomore chemistry course is Boyle's law. Boyle's law deals with pressure and volume. And basically, what he said is that if you multiply pressure times volume, you're going to get a constant. Okay? And if you think about it, we have pressure and volume. As the pressure increases, the volume decreases. If you're squeezing a balloon, the volume is going to decrease. So these two variables are inversely proportional. So the equation, because when you multiply them you get a constant, is P1V1 equals P2V2. Your initial pressure and volume will be equal to your final pressure and volume. And here's a nice picture. Here you have a balloon. As it's rising up, atmospheric pressure decreases. So here you have P1V1. Here you have P2V2. The volume's getting larger because the pressure's getting smaller. And if we plot V versus P, you're going to get this inversely proportional graph. Or you could plot it as 1 over P and get a straight line. Charles's law deals with volume and temperature. And basically, as you increase the temperature, your volume is going to increase. These two are directly proportional. So, since they are directly proportional, notice the slope of this line is constant. When you take the ratio, so your initial volume over your initial temperature should be equal to the change or the final volume over your final temperature. So if you cross multiply, because you don't like fractions, this is Charles's law. Now what's important is your temperature has to be in Kelvin. You'll find most of these gas laws you have to convert to Kelvin. Okay? And remember, in order to get Kelvin, you take degrees Celsius plus 273. And you notice the line here, if you extrapolate it, it crosses the 0 point here at negative 273 Celsius, which is 0 Kelvin, which we call absolute 0. This is where your particles stop moving, and they have basically no volume. So what happens when we combine different volumes of gases? Okay, so at a given temperature and pressure, so that means the temperature and pressure are not changing, then the volume of your gases that are reacting with each other will do so in small whole number ratios. So here you see you have 2 volumes, or we'll say 2 liters of hydrogen gas mixing with 1 liter of oxygen gas, and that's going to give you 2 liters of water vapor. It's just like stoichiometry here, okay? But remember, your temperature and pressure have to be constant. From that, we get Avogadro's law, which says that the volume of a gas at a constant temperature and pressure is directly proportional to the number of moles. So V equals some constant times N. So if you're comparing your initial, so you have your initial volume and your initial amount of moles, and then you say you change it to your final, the ratio of the two have to be equal. Okay? The more molecules of the gas you have, the more collisions, the greater the pressure. Okay? But in this case, we're talking about constant temperature and pressure, that your volume is proportional to the number of moles. And notice this number here keeps getting repeated. This is called your molar volume. So at STP, 1 mole of any gas is equal to 22.4 liters. Remember, STP is 0 degrees Celsius, or 273 Kelvin, and 1 atmosphere. So now, combining all these laws, first we get that the volume is proportional to 1 over P. Remember when we plotted 1 over P in volume, we got a nice straight line. Charles's law says the volume and temperature, so when we plotted volume versus temperature, we got a nice straight line. And Avogadro's law, when our number of moles increases, our volume increases. So if we combine them all together, we're going to get the ideal gas law, PV equals nRT, where P is pressure, V is volume, and it has to be in liters. N is moles, R is your gas constant, and T is your temperature in Kelvin. So here is your gas constant R. It depends on your unit of pressure. Remember at the beginning there was like 5 different units of pressure. It was crazy. So depending on what your unit of pressure is, so say your pressure is in atmospheres. This is your R value. Okay? Say your pressure is in pascals. This is your R value. Say your pressure is in torr or millimeters of mercury. This will be your R value. Okay? So how can we use the ideal gas law, PV equals nRT, to talk about the density of gases? Remember, density is mass over mass divided by volume. And looking in this equation, the volume is the same in both. So if I rearrange this for volume, it's mass over density. So wherever I see a volume, I'm going to put mass over density. So I have my pressure, instead of volume, it's mass over density equals nRT. Now N is moles, which is the mass divided by the molar mass. I'm going to use 2 m's for molar mass. So wherever I see an N, I could put mass over molar mass. So what do I have so far? I have my pressure times my mass divided by my density. My mass times my RT divided by my molar mass. And notice you have mass on both sides of this equation, so you could get rid of them. Now we could cross multiply and we get pressure times molar mass equals density times RT. I call this poom dirt because it's stupid and it'll stick in your mind. Poom dirt. Okay, so if I wanted to solve for molar mass, I would get density times RT over P. If I wanted to solve for density, I'd get pressure times the molar mass over RT. Okay. Now there is a special case with density. If you are calculating the density of a gas at STP, and this is only true at STP, it is equal to the molar mass divided by the molar volume. Okay, and that is only true, I need to emphasize this, okay, this is only true at STP. This works all the time. So if you want to forget this, that's fine. And just use this all the time, you will always get the right answer. So here, they're just using 1 capital M for molar mass. You get your density as the molar mass times the pressure divided by RT, or your molar mass is the mass times RT over PV. So here they plug back in volume, so it's slightly different than what we solved for on the previous page. So you could use the ideal gas law to get N, to get moles of what you're starting with. And then you could use stoichiometry. Say you're doing a reaction with this gas to find out the amount of products and reactants. Okay, so you can combine the ideal gas law with stoichiometry. So it's very powerful. So let's go over 2 practice problems here using the ideal gas law. So here you have a certain reaction that occurs and you produce an oxide of nitrogen as a gas. The gas has a mass, so here I wrote down my mass, of 1.211 grams. And a volume, here I wrote my volume, 677 milliliters, and I immediately converted it to liters because your volume has to be in liters. And a temperature of 23 degrees Celsius that I immediately convert to Kelvin because your temperature has to be in Kelvin. And your pressure is 0.987 atmospheres. Since my pressure is in atmospheres, I have to use the R that goes with atmospheres, which is 0.08206. Here is my equation for molar mass. So I plug in my mass times my R value times my temperature divided by my pressure times my volume. And I get 44.02 grams per mole. So then they say, what is the formula? Well, you know oxygen's molar mass is 16 and nitrogen is 14. So you just kind of have to play around until you get a relationship of these that adds up to 44.02. And it happens to be 2 nitrogens and 1 oxygen. The second problem. Here you're giving a volume of nitrogen gas, and it was collected in a tube at a temperature of 17 Celsius and a pressure of 737 millimeters. The next day, the volume changed, but the pressure was still the same. What is the new temperature? So since the pressure and the amount of your gas is constant, we could use Charles's law. Remember, Charles's law is such, but we want to solve for the new temperature, T2. So if you arrange this and solve for T2, you're going to get T1 V2 over V1. So by plugging in all of the numbers, you could get the new temperature. Okay? Here it was in Kelvin, and then I just subtracted 273 to get it into Celsius. So that is the end of Overview Part 1.